Sending rockets into space requires sacrificing expensive equipment, burning massive amounts of fuel, and risking potential catastrophe. So in the space race of the 21st century, some engineers are abandoning rockets for something much more exciting: elevators. Okay, so maybe riding an elevator to the stars isn't the most thrilling mode of transportation, but using a fixed structure to send smaller payloads of astronauts and equipment into orbit would be safer, easier, and cheaper than conventional rockets. On a SpaceX Falcon 9 rocket, every kilogram of cargo costs roughly $7,500 to carry into orbit. Space elevators are projected to reduce that cost by 95%. Researchers have been investigating this idea since 1895, when a visit to what was then the world's tallest structure inspired Russian scientist Konstantin Tsiolkovsky. Tsiolkovsky imagined a structure thousands of kilometers tall, but even a century later, no known material is strong enough to support such a building. Fortunately, the laws of physics offer a promising alternative design. Imagine hopping on a fast-spinning carousel while holding a rope attached to a rock. As long as the carousel keeps spinning, the rock and rope will remain horizontal, kept aloft by centrifugal force. If you're holding the rope, you'll feel this apparent inertial acceleration pulling the rock away from the center of the rotating carousel. Now, if we replace the carousel with Earth, the rope with a long tether, and the rock with a counterweight, we have just envisioned the modern space elevator, a cable pulled into space by the physics of our spinning planet. For this to work, the counterweight would need to be far enough away that the centrifugal force generated by the Earth's spin is greater than the planet's gravitational pull. These forces balance out at roughly 36,000 kilometers above the surface, so the counterweight should be beyond this height. Objects at this specific distance are in geostationary orbit, meaning they revolve around Earth at the same rate the planet spins, thus appearing motionless in the sky. The counterweight itself could be anything, even a captured asteroid. From here, the tether could be released down through the atmosphere and connected to a base station on the planet's surface. To maximize centrifugal acceleration, this anchor point should be close to the equator. And by making the loading station a mobile ocean base, the entire system could be moved at will, allowing it to maneuver around extreme weather and dodge debris and satellites in space. Once established, cargo could be loaded onto devices called climbers, which would pull packages along the cable and into orbit. These mechanisms would require huge amounts of electricity, which could be provided by solar panels or potentially even nuclear systems. Current designs estimate that it would take about 8 days to elevate an object into geostationary orbit, and with proper radiation shielding, humans could theoretically take the ride too. So what's stopping us from building this massive structure? For one thing, a construction accident could be catastrophic. But the main problem lies in the cable itself. In addition to supporting a massive amount of weight, the cable's material would have to be strong enough to withstand the counterweight's pull. And because this tension and the force of gravity would vary at different points, its strength and thickness would need to vary as well. Engineered materials like carbon nanotubes and diamond nanothreads seem like our best hope for producing materials strong and light enough for the job. But so far, we've only been able to manufacture very small nanotube chains. Another option would be to build one somewhere with weaker gravity. Space elevators based on Mars or the Moon are already possible with existing materials, but the huge economic advantage of owning an Earth-based space elevator has inspired numerous countries to try and crack this conundrum. In fact, some companies in China and Japan are already planning to complete construction by 2050.